Hello students. So in this lecture we will see the methods for bias stabilization, and in the last lecture what we saw that the base resistor method is not a good method for biasing because the thermal stability is very poor. The collector current increases 101 times faster than the collector reverse current or the leakage current. So this is not going to provide you a stable Q point. It is not going to provide you faithful amplification. So we have to find out new methods or new circuits for bias stabilization. The next method is collector feedback resistor biasing, and this is the circuit diagram, or better you can get these diagrams as I told you in any textbook. So this is another method. Why it is so called? Let me give you another diagram that will be sufficient, I think. You can consider any two of the diagrams. They are from different books. So this is the diagram, and the name and the term is collector feedback resistor biasing. Now what is this collector feedback resistor biasing? Let us study this. Let us understand this. So what happens in this case? You can see from the circuit diagram. First try to observe what is given in the circuit diagram. You can see in the circuit diagram that the emitter terminal is grounded, so it is a CE configuration. In CE configuration, you have to remember, I have told you in the previous lectures that the input current is the base current, the output current is the collector current. So what happens in this case? That one end of the base resistance RB, it is connected to the base, and the other end to the collector. You can see the diagram. This is RB. Its one end is connected to this base. This is the base, and other is connected to the collector end. This is the primary thing that you have to take care when you are designing the circuit. Now what is required? We require that the zero signal base current, the base current when there is no AC input, that current is not provided by the VCC as it was in the base resistor method. So the difference is that in the base resistor method, the base current was provided by this terminal VCC, or in this diagram this terminal, but here it is not so. Then from where you are getting the base current? You are getting the base current from a part of the collector current, which is the output current. It is the base current, the current flowing through the RB at zero resistance, at zero signal, input signal. It is being provided by this VCB rather than the VCC. This is the main difference. The difference from base resistor method is that the input current through RB is being provided by VCB and not by VCC. It was in the base resistor method, it was provided by VCC and not by VCC. This is the difference from the base collector method, base resistor method. Now we should understand why it is called feedback. What is the concept behind calling this as feedback resistance, feedback method, feedback resistor? So what you see here, that the VCB, it is forward biasing the base emitter junction. So the base current flows through the base resistor RB. This is how the input current at zero signal is flowing. When there is no input AC, the current is flowing through RB and it is provided by, not by the VCC but by the VCB. The input current flows through RB. So this is the main concept here. This is the difference. If someone asks you what is the difference, this is the difference. So in this circuit, what happens, it is called feedback system, or it is with collector feedback. It is because that the voltage for RB, it is derived from the collector. The voltage drop that is occurring across RB, it is due to a part of the output collector current. This current is providing some part of voltage drop here. So what this mechanism, it is called negative feedback. We will discuss the feedback mechanism and the oscillator in that section for oscillator. So some part of the output is fed to the input. This is called feedback. And it is a negative feedback effect that stabilizes the output current against any change in beta. So the concept is the current, or you can say the voltage across RB is provided by the VCB, or the current that is flowing through the collector. So some part of the collector current or output current is again fed to the input. This is the input and this is the output. Some part of the current flowing through RB, it is providing to the input or the base. The voltage across RB is provided by collector current which is output, and this is called a feedback mechanism. Which is a negative feedback mechanism. Negative feedback. Some part of the output is fed, part of output is fed to the input, This is called the feedback mechanism. So it is called feedback resistor or feedback method. What happens due to this feedback? That any change in the collector current in IC is stabilized against beta. Beta is IC upon IB, stabilized against beta. This is the mechanism. Now let us make this thing clear. Suppose by any mechanism, due to temperature increase or due to any mechanism, beta increases. This means IC by IB. This IC is increasing. If beta increases by some mechanism, and mostly the mechanism is temperature. It is the temperature effect due to which it increases. By some mechanism, then what will happen? If beta is increasing, IC is increasing, collector current is increasing, output is increasing. As a result, the load resistance is here, so ICRL is also increasing, However, some part is going to the, see what is happening here, it is all about conservation. So if the voltage drop across this end is increasing, what is happening? The voltage across this end, it is decreasing, because from the collector some part is going here and some part is going here. Since here there is an increase, here there is a decrease. So what is happening? The current through to the base, or the input current, base current is decreasing. But the voltage across RB, voltage across RB is decreasing, As a result, IB decreases. So any increase in IC is compensated by a decrease in base current. This is happening. This is the mechanism which is occurring. As a result, if IC is increasing and IB is decreasing, any change in beta, beta is IC by IB. So any increase in this quantity plus is accompanied by a decrease in this quantity. So beta is stabilized. Any change in beta is stabilized. Once beta is stabilized, your Q point will be proper, your Q point will be static. Now let us come to the equations and the method to find the stability factor. So the IC, collector current, is VCC by RL, or load resistance, and we have seen this in the previous section also. So this is the circuit diagram, and this is the saturation current, IC. Maximum current will be this much. Now the voltage across this end, in many of the text it is written VC, so I am writing VC. This VC you can calculate. It is VCC minus, this is VCC minus IB plus IC. IB plus IC into RL, the voltage drop that is occurring here. This is the voltage drop that is occurring here. So you can consider it as VCC minus ICRL, because IB is very less. So you can write it this equation in this manner. And from the lower part of this circuit, we can see that VC, this voltage, the voltage drop that is occurring here, in terms of the base emitter, which has to forward bias the base emitter junction, that is VBE plus ICRB, ICRB, because some part of the IC is providing the flowing through the base resistance. So this is the equation for voltage. Now you have two equations for voltage. Let me number them. This one is equation number 1, this one is equation number 2. Now you can equate these two. Equating 1 and 2. What we have? Let us see. Equating the two expression for VC, that is IBRB. Sorry, it is IBRB plus VEB is equal to VCC minus ICRL. RL is the load resistance. So this is the condition here. Now you can make use of this expression, IB is equal to IC by beta. This is the equation that we know. So you can replace IB by IC by beta. You can write IB, for expression IB you can write this expression, IC by beta RB plus VEB VCC minus ICRL. This is the equation. Now what we require, what we have to find out from this equation is the value of IC, because remember Q point is the point where we need the values of IC, collector current, and VCE. We have studied this. This is the definition of Q point. So from this equation you need to calculate the IC or the collector current, and this collector current IC is given by VCC by RL plus RB by beta. This is the value of VCC, sorry, IC, collector current. Now for this circuit, the stability factor you can calculate. I have told you the alternative expression for the stability factor, and the stability factor S is given by VCC by RL plus RB by beta. Now you can see that these two equations are same. So this is the stability factor. Now in this case, this is very interesting that the two equations, they are same. The stability factor and the IC, the collector current. So in this case, mathematically it has been found, you don't need the derivation, that S is less than 1 plus beta. So what we get? We get an improved stability factor compared to the base resistor method. Improved stability factor. In that case it was equal to 1 plus beta, and it is a quite large value. S, which is less than 1 plus beta compared to the base resistor method. Compared to base resistor method. So this is one modification that we get in the collector feedback type of biasing. But still this biasing is not proper. Still we have still it is not very satisfactory, I should say. If you calculate from the circuit analysis the requirement, the base resistance, because during the experiment I am telling you again that you have to make the calculations first, then you have to proceed for the experiment. The value of RB, the base resistance required for this type of biasing is, RB is VCE minus VBE, base emitter voltage, by IB. You have to fix this IB to some value, and then you have to calculate the base resistance. This can also be done from the circuit analysis. This is the value of base resistance that you require for this type of biasing. So you have to take care, you have to do the calculation first and then proceed for the experiment. This circuit provides good stabilization because it is, I should not say it is good stabilization, it is better than the base resistor method, but still it is not good because its stability factor is less than 1 plus beta, and beta is quite large quantity. It is not equal to 1 plus beta. If beta is 100, base resistor method it would provide 101, this may provide 98, 99, still it is not good. So the operating point will change, but it will change less than the base resistor method. This circuit again, it is providing a negative feedback, and negative feedback reduces the gain of amplifier. We will discuss the feedback mechanism. So there are two disadvantages. S is still not satisfactory, It is less than the base resistor, but it is not good. And second, negative feedback reduces gain. The gain is reduced in negative feedback. So your amplification will not be proper. It will not be a good amplifier. So what are the other methods that are available to us? What are the other circuits? So we should now consider the mostly used circuit for bias stabilization, that is called universal circuit, and that is called the voltage divider method. This is the circuit that is mostly used, and it is also called universal bias stabilization circuit, and it is mainly used for the integrated circuits where the transistors are used. We will see what it is, why it is called voltage divider. So this voltage divider circuit, voltage divider stabilization circuit, stabilization method. Because there is another method, emitter feedback, that is also involving feedback, and negative feedback is going to reduce your gain. So it is still not very satisfactory method. So what we have here, let me show you the circuit diagrams. Both are same. For your convenience, I am providing the circuit diagram in two ways, shown in two ways. The connections are same. So these are the two circuit diagrams of the voltage divider method. This method is called universal stabilization circuit, universal bias stabilization circuit, called universal bias stabilization circuit. It is called voltage divider because what we have here, you can see the circuit. There are two resistances. I will tell you what are the precautions that you have to take in this case. You have two resistances, R1 and R2. The voltage, it is divided between two resistors, and this is this arrangement across the VCC. It acts as a potential divider. The potential is divided across R1 and R2. It is called voltage divider. As the potential is distributed between R1 and R2, is distributed between R1 and R2. So it is called voltage divider method. You are dividing the voltage between two resistances, R1 and R2. This is the main concept here. So it is called voltage divider. Now the voltage drop that is occurring across the second resistor from VCC, this voltage is divided between R1 and R2. This one is providing the forward biasing of the base emitter. This one is providing the reverse biasing of the collector base. R2 forward biases the base emitter junction, and R1 reverse biases the collector base junction. This is how the circuit works. So it is called voltage divider. Now in this case, what you have the voltage divider theorem. You need not derive that theorem right now. You will just make use of this circuit. Before going to that section, let us discuss some more things. So these R1 and R2, you have to connect them across the VCC. The base resistance, the emitter resistance RE that provides you the stabilization. This RE is providing the stabilization. These are some important points of this circuit. Provides stabilization. RE, the resistance across the emitter, provides stabilization. As I told you, voltage divider means it is dividing the voltage between R1 and R2, and they are biasing the junctions. Now let us see the analysis in the most simple way. What we require? We require the collector current. And I will go through the most simple method, IC. Now this IC we can calculate it because there are two resistances. So you can see the diagram here. I1 is the current that is flowing. So I1 is VCC supplied from VCC and R1 plus R2. This is the collector current I1, and voltage across resistance R2 you can find out. Voltage across R2, that is forward biasing. R2 you can write VCC by R1 plus R2. This is the current flowing in times R2. This is the voltage across R2. This is forward biasing the circuit, emitter base junction. Now the voltage V2 you can apply the Kirchhoff's law. It is VBE plus, let me provide you the circuit diagram here. VBE plus it is VE plus it is VE. This is the voltage at V2, or you can write V2 as VBE plus IE, emitter current, and emitter resistance. This one is the emitter resistance that is stabilizing the circuit. You have to remember this. So this is, from here what we can calculate? We can calculate I, because we have to find the coordinates of Q point. You need IC and VCE, and IC is almost equal to IE. So if we calculate IE, we can calculate IC also. So IE is V2 minus VBE by RE, and this is approximately equal to IC. So you have calculated IC. And the most interesting thing that you can see from this expression, there is no beta. This beta is the parameter that creates instability. So there is no beta in the analysis. So it is free from any temperature fluctuation. The collector current, it depends on VBE, base emitter voltage, and in practice V2 is much larger than VBE. So you can write IC as V2 by RE. Simple equation. It is independent of the transistor parameters, and so it is providing the most satisfactory stabilization. Similarly, you can calculate the VCE, and this VCE comes out to be, I am directly writing the result to save time. You can calculate applying the Kirchhoff's law, VCC minus IC into RC plus RE. This is the VCE. Now you have got the two coordinates of Q point. These are required. And you see in none of the quantities, collector current and the collector emitter voltage, there is beta is absent. So it is independent of all transistor parameters. VBE is also not there. So this circuit provides the best stabilization among all methods. Best stabilization, voltage divider method. The stability factor, in this case the stability factor S, it is also a very interesting quantity. stability factor is equal to 1. I will show you later on the calculation if you require. It is S, or let me do it here. S is 1. How S is 1? Let us see how it is 1. You can use the definition of the stability factor. I have told you the definition: 1 plus beta into, you have R naught plus RE. This is the expression that we use. Output resistance, R naught is output resistance, and then it is R0 plus RE plus beta RE, and this R naught is R1 R2 by R1 plus R2. This is your R naught. Now you can put the value of R naught here, and you find that S is equal to 1. Stability factor is 1, and this is the best stabilization circuit among all the methods. It is totally independent of the transistor parameters. Now there are certain additional points when you are doing the experiment that I will tell you in the next lecture. And the last method for this biasing, which is generally used along with this voltage divider method. So I hope the things are clear. If there is any difficulty, if there is any problem, you can ask me. I will discuss those issues if you have some in the next lecture. So for the time being, stay tuned and watch the lectures, and if you have some problems, then please comment and tell me where you are feeling difficulty. Thank you.